Question already.
Hmm? What is non-liquid Fermi liquid?
I guess we will hear in a second.
That's what the talk is.
So I think since we just had a colloquium by John yesterday, I don't think I really need to introduce him. But I have to say that I'm very excited to hear a talk about gapless QFTs. Many QFTs become gapless at high energy. So this definitely, because of that, if nothing else, fits into the hydrogen theory lunch. So go for it.
Okay, thank you. Thank you. Thank you for having me. I promise that this is a talk about field theory. That's the subject. And so yeah, I feel okay about about talking about energy lunch about this. And yeah, so more specifically, it's about a very gapless field theory. What I mean by that is it's a field theory that has both a Fermi surface, meaning some locus and momentum space where there are gapless fermionic degrees of freedom, and a Bose surface, meaning some locus and momentum space where there are gapless bosonic degrees of freedom. So even more gapless than a Fermi liquid. And our goal is to understand a certain it's a certain critical theory for a transition out of a Fermi liquid phase. And it's based on work with my colleague Tarun Grover. And I think this number might be ambitious. I don't know. We'll see. The paper. Yeah. Okay. There's a paper. Hopefully it'll appear. And so, okay, let's begin with a moment of appreciation for Fermi liquid. So yeah, Fermi liquid is an amazing thing. It's despite the fact that it has all these gapless modes on a Fermi surface, it nevertheless describes essentially a phase of matter. A robust property of a phase of matter. And I guess there are at least two useful points of view on this stability. One is Luttinger's theorem, which assuming we have translation symmetry and particle number conservation, protects the volume of the Fermi surface from whatever you can do to it. And so the volume enclosed in a momentum space by the Fermi surface is determined by the number of particles. I don't know why that happened. Okay. Yeah. Okay, let's try again. Okay. The second point of view is a renormalization group point of view, which I learned from Polchinski and Shankar, which is the statement that the Fermi liquid is a fixed point of the renormalization group, which in itself, this is a remarkable thing because it means it's scale invariant, despite the fact that it comes with an intrinsic scale, namely the Fermi momentum, the radius of the Fermi surface. The Fermi momentum is the momentum, and yet the theory is scale invariant. So how is that possible? Well, the idea is that the momentum transforms under scale transformations in an unfamiliar way. Rather than scaling to zero, the momentum scale towards the Fermi surface. Okay, so it's a sort of intrinsically non-Lorentz invariant kind of scale invariance, but nevertheless it describes a fixed point of the renormalization group, which moreover is stable and there are almost all perturbations. Right. So one way in which we know we can kill it is by breaking the particle number symmetry. Right. So that is if it can become a superconductor, and indeed the one direction in which it's direction in which it's unstable is to becoming a superfluid. But the fact that only this one direction is only marginally relevant is really quite a remarkable thing. The generic four Fermi interaction is irrelevant, and only very special four Fermi interactions, namely forward scattering, where the set of momenta that come in is the same as the set of momenta that go out, are marginal. Okay, so that was a moment of appreciation for the Fermi liquid, and now let's try to kill it. Okay, so the question I want to address is, how can we leave this phase that I just told you has this nice robustness? And so one way is superconductivity. I'm not going to say much about that. Let's think about some other ways. So one way to evade the Luttinger theorem is to simply drain the Fermi sea. Right. So here's a picture. Let's start here. Here's some band structure as a function of K. If I put the chemical potential in the middle of the band, I get a metal. I get a Fermi liquid if it's weakly interacting, and actually much more generally. But then if I change the chemical potential so that the chemical potential is in between the bands, then there's just nothing. Right. This is boring. Right? This is not what I want to talk about. Okay, that's cheating. Much more interesting is and something that's been studied a lot, in particular by Andre, is a spin density wave. So that is if somehow there develops in the system some bosonic mode that carries spin, and condenses at some finite wave number, then so this word mutilate is due to, I learned from Senthal, it can damage the Fermi surface by connecting special points on the Fermi surface to each other, they're called hot spots. So it changes the shape of the Fermi surface, but there's still a Fermi surface left over it because away from these points, far from these points, basically the gapless modes don't see the thing that happened. So perhaps more interesting is if we take this wave number Q to 0, so that's something like a ferromagnet, but in that case, actually, it's really the same as what I described. It just, you just separate the two spin species. Okay, a more interesting attempt to kill a Fermi surface is I learned about it from Senthal, is the following. Okay, let's start here. So I'm going to tune some parameter R. I'm not going to tell you exactly what it is, but so we started in a Fermi liquid, and let's imagine. Okay, I'm going to try to describe this in high energy language. Let's imagine that secretly the electron is a meson, meaning some gauge invariant composite of some degrees of freedom, which I'll call B and F. So that is, I'm going to write the operator that creates the electron as a product of B and F.
What you mean, like meson or barren?
Well, okay, my gauge group is just U1, so maybe there isn't such a big distinction. Yeah, some gauge invariant composite. And so what I'm describing, it's called the part-time construction. It's a way to get a picture of various interesting phases, but here's a way to get a picture of this familiar phase. So let's suppose that this degree of freedom B forms a superfluid. So B condenses, meaning it has some non-zero expectation value. It exists the U1 gauge theory that I just introduced, and essentially you can say psi equals F, and what's left is just the Fermi liquid. Okay, so now imagine that the dynamics of this B field is such that there's some parameter R, which tunes it from its superfluid phase to some insulating phase. Right, so a boson can undergo a superfluid insulator transition. And so if B forms instead an insulator, so essentially the expectation value of B is 0, so psi is not just the same as F, but F is still always describing a Fermi liquid, we get some much more interesting state where there's an invisible Fermi surface, right? The thing, so if I created an electron, I have to create both a B and an F. But B has, the correlation functions of B are like those of a Mott insulator. The Fermi surface is invisible to direct probes of the electron. Of course, you can still see it in thermal things, and so in this way, we make an insulating phase that nevertheless has this secret Fermi surface. The original Fermi surface is in some sense gone. Okay, so I mentioned this as for context that this is an interesting way to kill a Fermi liquid. What I'm going to do today is much less interesting than this. I'm going to do the following thing. Let's suppose that the Fermi liquid I'm starting with is a liquid Fermi liquid. Okay, what I mean by that is it's living in the continuum, right? So it's something that you can make just by taking a bunch of fermions, like lithium 7 atoms, and putting them in a pile, right? Just fill a box with them. So there's no lattice, no underlying lattice. The system is really isotropic and homogeneous. And imagine they can form some Fermi liquid phase. And now the question I want to ask is, so let's let those atoms interact with each other. Okay, I just described in terms of atoms just as a.
Why do you say lithium 7 is a fermion?
Is it 6 that's a fermion?
Electrons and
is it 6? It's 6.
Nucleus has a spin free out.
Sorry, it's 6. It's 6. I meant 6. Sorry. Sorry. I got confused by Matthew Fisher is the reason, because he's been studying this lithium 7. My apologies. Thank you. But I mentioned the call atoms just to have so you can have a very vivid example of what we're talking about in mind. It could be electrons in some other system. But now let's imagine that they have some short range interactions with each other such that they form a solid. Okay, that's the supposition on which everything is based. Suppose that they somehow solidify as a result of interactions between each other. Let's ask what happens. So yeah, so the thing I'd like to study is what can the critical theory of such a transition be, if indeed the transition is continuous or something close to continuous. So that's the question I want to think about.
How are you defining solid? Is there broken translation symmetry in that state?
Yeah, that's what I mean. Yeah, so translation is broken down to some crystal.
So it's a Wigner crystal.
Yeah, if indeed, if we were talking about if the fermions that I was talking about here were a gas of electrons, yeah, you would want to call it a ring of. Yeah. So one.
Tell me what I'm saying is too much condensed matter. But if you start with the Fermi,
Mhm.
you can classify Q equal to zero instabilities in terms of various angular momentum.
Right. I want to talk about a Q non-zero instability.
You're
Yeah.
about finite Q.
Finite Q. Yeah. Good. So that it forms. Yeah. So
Right, that's
Yeah.
the question of whether it forms after the transition or right as the transition.
I want yeah, right at the transition. Good. So now, I'm sure some of you are thinking the following thing, that why don't condensed matter physicists spend all their time thinking, liquid solid transitions happen all the time. Why don't we hear all the time about people studying the critical theory of liquid solid transitions? And the answer is that everybody thinks they're always first order. They're always first order transitions, and there's nothing to say about the critical theory. You just jump from one phase to the other. And there's a good reason that people think that. And it's an interesting field theory reason, and let me explain. So let's invoke Landau and think about what is the effective field theory in the neighborhood of such a continuous transition. So suppose that there's a continuous transition between the liquid and the solid, and let's think about what are the degrees of freedom near the transition. So for now, let's forget about the fermions. We just have some particles. Somehow they conspire so that there's some collective mode with some non-zero wave number, which I'll call Q naught, that wants to condense into a lattice, right? If I condense a mode with non-zero Q naught, I get some density wave, right? And I want to make some like interlocking density waves to form maybe a square lattice. Okay, so what's the nearby effective field theory? Well, there's the key degree of freedom is the order parameter for this transition, which is some mode of a boson, just like the density of these atoms. And the key thing is that its dispersion has the following form. Right? So forget about the omega for a second. So it looks like the bottom of a wine bottle. So this is momentum, and the thing I'm plotting here is the energy of a boson mode with momentum k. Right. So at non-zero r, it just says that there's a minimum at some non-zero value of q, non-zero magnitude of q. And as I take r from positive to negative, that minimum goes through zero. Right. So it's like this ring of modes is becoming massless and then wants to condense. So a little more about this. Within the liquid phase, you can already see that there should be such a ring of minima in the boson dispersion relation, because think about the static structure factor, meaning that the 2-point function of this boson. In a liquid, it looks like this, right? There's a big peak at the at the average separation of the atoms, and so this thing is basically the inverse of this. It's just the propagator for the boson, right? So this thing, the fact that this thing has a minimum at Q naught says that this thing has a peak at Q naught. And I'd like to emphasize that the fact that there's really this ring of minima it's very important that the system is isotropic, right? I'm assuming rotation invariance. There's no I'm ignoring any underlying lags. Okay, so the idea is as I tune R from positive to negative, I go from a phase where rho Q wants to be 0 to a phase where the system spontaneously chooses some crystal axes, right? So at the critical point, every mode whose wave vector has magnitude Q becomes massless. But beyond that, it picks out some particular Q directions and condenses those, and thereby forms a solid. Okay, so the key point is that at the critical point, it hasn't yet decided in which directions the crystal axis points. So okay, so that's the Landau theory. Now, why is it wrong? Why is it not the right critical theory? Well, there are two good reasons for this, the lore that such a transition is always first order. And the first one is that, so yeah, there's this potential for rho, which I didn't say anything about, which determines the energetics of what's happening. And in the absence of any extra symmetry, that potential can have a cubic term. And as you probably know, if you have a cubic term in the Landau theory, then rather than the two vacua on the coalescing as you cross the transition, you just jump from one to the other, right? It's a first order transition. And so how I'm going to deal with this cubic term is, well, I guess there are some options. The short answer is I'm going to ignore it. And the reason I'm going to ignore it is either that I'm imagining that the transition is weakly first order, and I'm choosing the value of the cubic term to move towards the critical point. And I'm going to be interested in, sort of intermediate scale physics will be governed by the critical theory that I'm interested in. Or we can cook up some situation where there's a symmetry that forbids it. So not exactly the solidification transition that I've advertised, but something that is governed by the field theory that I'll talk about. Okay, I'm sure we'll talk more about the cubic term. But there's a second, much more interesting reason that this critical theory, that you don't hear about this critical theory all the time, and that's that it's not self-consistent in the following sense. So let's think about a finite temperature liquid solid transition. And let's ask, within this theory, so yeah, put this thing at finite temperature, meaning, yeah, make the Euclidean time periodic. And think about the correction, the renormalization of this coefficient, right? This coefficient R is the thing we're tuning through the transition, right? That's like the mass squared of this field. And I want to approach the transition, I want to take R towards 0. Okay, so the only assumption I'm making here is that there is some quartic coupling in V, so that we can write a vertex like this where the boson couples to itself, and so we can draw this diagram. And using the propagator for this boson, so the key thing is that this parameter R that we're trying to tune to 0 gets renormalized by this whole sphere of gapless modes. And each of these modes behaves as if it's one-dimensional, right? Because the dispersion only depends on the direction transverse to this Bose surface. So it only disperses in one direction, and so this becomes a one-dimensional integral over Q. And as you can see, it's infrared diversion. So that is, it's cut off by the size of the box that you put the system in, and yeah, it grows with the system. So you thought you were near the critical point, but the fluctuations of the would-be critical theory drove you away from the critical point. So it's just not possible to sit at the critical point. It's a pretty weird phenomenon, I think. And so that's why people say that such transitions are always weakly first order. And so let me change the question a little bit. Yes.
If I may interrupt, please. This formula is known formula. Assume that you already integrated over frequency if it's 0 temperature. So
yeah, it's 0 temperature. Yeah, so you can imagine the frequency was never there. Yeah.
But you used propagating boson, omega squared. What about
no, the omega squared doesn't appear in this calculation, right? So it's just the contribution of the 0 Matsubara.
But then it's
thermal, yeah, exactly. This is thermal.
Finite temperature.
Finite temperature, exactly. Yeah, so good. So you're exactly asking about the next step. I'm going to change the problem in 2 ways. First, I'm going to ask about 0 temperature.
Okay.
Right, so 0 temperature, we get 2 integrals. We also integrate it for omega, and now it's only a log divergence.
Assuming that it's omega squared, but not lambda without mod omega.
Exactly. Okay, so you also anticipate the next point, which is what happens if we also couple to a Fermi surface. Great. So as you can see, if we couple to a Fermi surface, the boson is Landau damped. It's instead of omega squared, its dispersion is mod omega from the loop of the fermions, or normalizing the propagator of the boson. And now if we do this calculation, we find a finite answer. Okay, so the point I want to make is with these 2 modifications, if we ask about a solidification transition that happens at 0 temperature, and in the presence of a Fermi surface, this argument is gone. It can be continuous. Okay, so let's try to see what happens. So that means there can be such a field theory, and let's try to understand that field theory. Okay, now before I talk about the field theory, I need to say a little bit about what the transition is to. Right? So yeah, my interest is really in this critical point, but I suppose it would be useful, for example, if we want to look for consequences of this critical point in experiments, probably we should know what's on the other side. the transition, what phase is sitting there. And so I said, it's a solid, but what kind of solid is it? What is, so for example, is it also a metal? Is it an insulator? Does the Fermi surface survive? And okay, so before I get to that though, I need to say I want to say something about scales in the problem. So I said that the Fermi liquid is a remarkable thing because it's scale invariant despite the fact that it has a scale. Right. So sometimes this phenomenon is called hyperscaling violation, because it means that you can't just use dimensional analysis everywhere, because factors of KF can sneak in and change your like relations between critical exponents. The theory I want to think about is this Landau theory of rho that we were talking about. I guess I did write it on the previous slide, some kinetic term for the Fermi liquid, and then a coupling to them, which is this kind of Yukawa coupling, right? Just as if rho is the density of the fermions. And the critical theory that we want to talk about also should be scale invariant, but now it actually has two momentum scales. In addition to the Fermi momentum, and in addition to KF, there's also the radius of the Bose surface, this Q naught, this parameter Q naught, which is also a momentum scale. And so now something else happens, which is that you can make a dimensionless ratio of these two intrinsic scales in the problem, it's really weird. And so one way to think about that dimensionless ratio is it determines which points on the Fermi surface are coupled by critical boson modes. So here's the picture of the Fermi surface. So this is a circle of radius KF. I'm thinking about 2 + 1 dimensions. And let's think about a boson mode, sorry, a fermion mode at this point on the Fermi surface. By that Yukawa coupling I wrote, I want to conserve momentum, with which other points on the Fermi surface is it directly coupled? And so that's the intersection of the Bose surface centered at this point with the Fermi surface. So that's these 2 points. Okay, so you see that if I specify the radius of these 2 circles, it specifies an angle, which I'll call theta naught, which is related by this trigonometry. So theta naught is the angle between points on the Fermi surface, so these 2 or these 2, that are connected by a critical boson. Yes.
I'm very used to seeing Fermi spheres. Can you remind me the definition of a Bose sphere? What do you mean?
Yeah. So I mean.
I know you probably just explained it, but I must have not absorbed.
Yeah. So just as Fermi surface is a locus and momentum space where there are gapless fermion modes, Bose surface is locus and momentum space where there are gapless boson modes. And why is there a Bose surface? Well, it's because of exactly this picture, that when R is equal to 0, every mode whose Q has magnitude Q naught has 0. Yeah, gapless mode. Ring of gapless.
Special feature. So you wouldn't expect it in like a random atomic field theory. This is a feature of this particular effective field theory.
It's okay. So yeah, what
I'm trying to. The Fermi surface is very generic. You turn on chemical potential, bang, you got it. Here, this is something special.
Especially because Q naught is non-zero. So there's separate story how to get this form of boson propagator, which is picked at finite Q naught for translation and rotation invariant systems. But suppose you get it, then everything.
the starting point of what I'm doing. Suppose that you get this, then we're going to see what happens. But yeah, so the way I motivated it is indeed it's the Landau theory to this solidification transition, right? So what are the ingredients? The ingredients are I have this bosonic mode that wants to condense at some non-zero momentum, and it's very important that I assume rotations. So at the critical point, it hasn't decided the direction of the momentum. That's my analysis.
Can I just check my understanding? So like the reason this is all happening is because to go from liquid to a solid, you gotta break the symmetry.
You gotta break translation symmetry.
Translation symmetry. So you gotta pick out a vector that's Q naught.
Q naught is the magnitude of
The magnitude of the
yeah, and the key point is you haven't decided which direction.
You haven't decided the direction, but anyway, you do have that scale in the problem.
Right, this is exactly what you said. The non-trivial element of the series is the presence of the scale Q naught in rotational and translation invariant system. This by itself requires some non-elitistic and there is one function, etc.
Okay.
In particle physics, isn't it just the compact direction associated with the Mann-Goldstone boson and the symmetry you're non-linearly realizing?
Well, I think it's a bit different. So this the wine bottle appears in many places. It's important that the axes of this picture are the momenta of the boson, right? So that not the field. this is not the potential for a field.
So the symmetry here is explicitly broken.
Translation symmetry
Yes,
is the symmetry that's
explicitly.
being broken.
It's explicitly broken.
No, spontaneously
But
broken.
but
Yeah.
it's spontaneous, the symmetry should still appear in the system, and there should be some.
That's correct.
Some
Yes,
flat direction.
absolutely. In the solid phase, the translation symmetry is non-linearly realized, and there are gold star modes, which are the phonons of the sun.
And that's what, okay.
Yeah,
But it's
but,
not.
but the interesting
the
thing.
phonons are not going around the bottom of that.
Well, so, okay, so in the phase, you pick out particular directions along this thing, and the phonons are the fluctuations about, so the phonons are a subset of these modes that are addressed. At the critical point, it's like the phonons for every possible direction are gapless at the center. Good, yeah, thank you for the question. Great. So, okay, so this is the, so we have this ratio, we have these two momentum scales, despite the fact that the theory is scale invariant, and the ratio specifies this angle. So sometimes I'll parameterize things like that. And so it's a very funny situation. So that's why in my title, I called it a family of very gapless field theories, because it's parameterized by this, by this theta naught, this angle theta naught. And as we'll see in the renormalization of the theory, I don't think we should think about it I don't know how to think about it as a marginal operator. It's really like just a parameter in the theory. Okay, now you can see that there's an upper bound on this ratio in order for this picture to look qualitatively correct. If I make if Q naught is too big, too big, then it doesn't connect points on the Fermi surface at all. Right? If this blue circle is so big that a point, if it's centered at this point, it doesn't touch any other points, then the story is very boring. So yeah, so there's an upper bound on this ratio, which is actually when the sign. That's interesting, actually. So then, the sign is equal to 1 then. Yeah, that's a special point. I haven't thought about it carefully. Yeah, okay. Yeah, that's an interesting question. I haven't thought about that. Okay, so good. So what's the nature of the solid phase? And so here I need to ask a sensitive question, which is why are solids commensurate? Meaning when you make you have a bunch of atoms, they spontaneously form a solid. Why is it that there's one atom at each lattice site, as opposed to having some atoms left over at the end? Some remainder number of atoms, and maybe there's a good reason. And let me try to say something about what I think the reason is. So here's the picture. I want to ask, what is the phase immediately to the left of the critical point, where we condense this mode rho q and form a solid, but with small amplitude, right? And one way to think about this, so there's a sort of mean field way to think about this, where how does this mode rho q couple to the Fermi? Well, it's just some periodic potential, right? There's some rho times psi bar psi coupling, and I'm just going to set rho to its expectation value. So it's just free fermions in a periodic potential. And the tricky thing is that the question we need to ask, the question of why are solids commensurate, is what is the lattice spacing, right? What is the period of the potential? And of course, in the actual system, that's a dynamical variable, right? The lattice spacing of the solid is something that's dynamically determined. And you see that lattice spacing is determined by Q naught. And in the case of one dimension, there's a very clear answer from this point of view, because if I couple these fermions to a periodic potential, the thing that happens is, so initially they had some k-squared dispersion, but as a result of the periodic potential, this is a problem you can give your quantum mechanics students. The mode, so that the potential centered at k equals 0 hybridizes with the potential centered at k equals q naught, and so there's avoiding crossing, and the key point is that the dispersion goes down relative to the free dispersion. And so if you choose the lattice spacing so that you exactly fill the bottom band, you lower the energy. You lower that. So essentially, this is the same as Peierl's argument for why 1D chain would prefer to hybridize Yeah, the Pyro's argument for his instability. And so if you ask for a given KF, what value of Q naught minimizes the ground state energy, the answer is the one where it's an insulator. So if the lattice, the lattice spacing is chosen so that the system so the system is an insulator because it minimizes the kinetic energy of the fermions. Okay, that's what I just explained. The analogous argument actually doesn't quite work in higher dimensions, and that's because if I take this k-squared dispersion and couple it to a arbitrarily weak periodic potential, the thing that happens is I get a bunch of bands that inevitably overlap with each other, right? So the bottom band, parts of the bottom band have higher energy than parts of the second band, and so the thing you get is metallic. The thing you get still has a Fermi surface, and so I can't quite say that the thing I'm doing is killing the Fermi surface so that it's completely gone by the solidification procedure. Okay, so and also I can't quite say that this dimensionless ratio Q naught over Kf is determined by making the thing an insulator. It's quite I feel quite awkward about it. So the statement I'm making is whatever Q naught over Kf is determined somehow that I'm not answering. The transition, at least if you believe this mean field calculation, is to a solid metal. It has Fermi pockets. There's an alternative possibility, which is let me embrace the rho cube term that I said I was going to ignore. So in the presence of the rho cube term, the transition is at least weakly first order, and so immediately on the other side of the transition, we can jump to a phase where the magnitude of rho is not so small. And if the magnitude of rho is not so small, we can the perturbation of the bands is bigger, and it can easily be that the bottom band is separated from the other bands and so you can form just a band insulator directly. And so this is the scheme by which one can find a sort of a weakly first order transition between a liquid metal and a solid insulator that has no Fermi surface at all. So it's really just a bad insulator, really vegetable of the theory. Yeah.
Very good question. If you go into band insulator, you lose Landau down immediately.
That's correct.
Don't
Yes.
you go back then to what you started with, that then you will have divergent corrections?
Well, okay, that's why I draw this wiggly red line, right? Because my statement is that this can only happen if the transition is at least somewhat first order. All right, so you jump to a band insulator, you're no longer at the critical theory. So my statement, however, the critical theory that I'm going to talk about can still tell us something about behavior at length scales in between this correlation length that you get from the fact that it's weakly first order and the cutoff. So it's, how to say, weakly first order transitions do have universal physics. Right.
I'm more concerned about that you are away from the transition, that if you are in the insulator regime, then you have omega square, and then you go back to the issue that they have Goldstone modes, and then they're not overdone.
But that's a problem for the critical theory, right? So the reason that's a problem is because it renormalizes the
True.
the critical theory. Yeah.
Now, maybe I have to reformulate the question.
Yeah.
If you are inside the solid.
Yeah.
For this particular situation,
Mhm.
when the number of Goldstones is actually infinite.
Okay.
Don't you get singular corrections within the theory just because you have, as you said, you have arbitrary direction of Q, which is still a.
No, I think right at this point, you've already picked a direction, right? You picked a direction.
That has Goldstone mode.
There's ordinary,
It's a transfer
just
theory.
phonons of the solid.
Mhm.
Yeah, those are just the phonons.
But the fact that there are many of them, does it affect the
I don't-
theory? No?
I think it's just ordinary phonons of a band insulator. Yeah. That's what I think.
Okay.
Yeah. Okay. So these are two ways in which this field theory that I'm going to describe could be used. These are two phase diagrams, which if you see them in your experiment, you might think about the critical theory I'm going to tell you. Yes, Alexei.
Is there a reason to take field theory seriously at that point? Should you expect some systems or will actually work?
I think so. Because the thing I'm relying on is that the effective field theory that I described is the right thing, right? Because, otherwise, who knows what I'm talking about? And the fact that near the transition, the amplitude is small, right? Near the,
Which amplitude?
the amplitude of the order parameter, the amplitude of the order parameter. And that's
basically the assumption that it's continuous, basically.
Yeah.
Yeah, and then you're trying to kind of get self-consistent.
Yeah, that's right. Yeah, we actually did spend some time asking ourselves, we very badly wanted to go directly to an insulator. So we spent a long time trying to get around this conclusion, and I think it is actually pretty robust, unfortunately. Yeah. Okay, so when I draw pictures, I'm going to choose the value of Q naught over Kf for the case where the solid is a square lattice, and where the lattice spacing is determined so that it's commensurate, so that you can form a band insulator at that lattice spacing. And so that's the condition that the volume of the Boron zone is equal to the volume of the Fermi sea, which is the condition for what's called squaring the circle, right? So this is something that's famously impossible to do with a straight edge and compass. And so actually this was the initial title of our paper, squaring the circle, because what we were trying to do seems similarly impossible. But unfortunately, yeah, it's yeah, we think that Q naught over Kf is actually not fixed to this value. Actually, since this is a high energy talk, maybe I'll make one more comment. So this parameter Q naught over Kf is very strange, right? It seems like it's a dimensionless parameter of this critical theory. On the other hand, I think it's a bit like the strong CP problem. Okay, bear with me for a second. In that, the theta angle in QCD is some dimensionless parameter of the theory, which if you only knew about the standard model, you would say, well, there's this problem that it could take any value, but the neutron electrodipole moment seems to be zero, and so it has to be zero. The way we solve, well, one way that we try to solve this problem, at least until Alexei seems to ruin the solution. Okay, is by imagining some high energy physics where this theta angle becomes a dynamical variable, and the dynamics of QCD itself generates a potential whose minimum is at zero, right? And so I think it's a similar thing, that we have this theory which has this apparent arbitrary parameter, but in the true theory, in the more microscopic theory, the theory of like electrons interacting with some potential, it's a dynamical variable and it's determined by energetics.
But it's not periodic.
No, it's not periodic. No, it's different in that sense. Yeah.
Sorry, I'm moving from it, yeah. So you started the situation when everything was rotational in bed.
Yes.
And this is how you get rotational in bed forming bosonic propagate.
Very important.
Now it's square wave.
No, that's the lattice that I formed spontaneously.
Sorry?
I'm just assuming that the lattice that I formed spontaneously is a square lattice. Yeah. It's not well, I don't think it's an important assumption. Yeah. Good. Yeah. So indeed, Wigner crystals are often seen to be triangular. Probably.
So you just choose the modulus of Q naught as particular relation with K.
That's what exactly. That's what I'm intending to convey by this picture. Exactly. Okay. So and one important point about that particular value, and in fact generic values, is that this angle theta naught that connects by which points on the Fermi surface are connected by critical bosons is an irrational multiple of 2 pi. Did I say that the right way? Meaning that if I start here and move by an angle theta naught, and then move by another angle theta naught, okay, that's what I tried to draw in this picture. I drew, started at some point, moved by theta naught, moved by theta naught, moved by theta naught, moved by theta naught. So and each of these things are the Bose surface centered at those points. You can see that we completely cover the Fermi surface. So every point on the Fermi surface is coupled by a series of interactions with the critical boson to every other one.
But you can tune it, I guess, to make it rational.
For special values, it could be
Do they
rational.
have some extra
Weird things
meaning?
happen.
I mean, like it's some enhanced symmetries, or what does it mean?
Well, so then it becomes much more like the spin density wave transition, where they're just each points are connected only hotspots, or they're only connected in groups. I don't know. So we studied the generic case. Yeah, there may be something to say about special cases. Okay.
Question. To
Please.
see if I'm understanding
Please.
correctly. So at least I was thinking that Q naught is a parameter that's like inherent to your theory versus KF is about like the matter you put in. So in the example of like the lithium, like Q naught would be related to, interatomic spacing with lithium. So it has to do with whether I put in lithium or some other atom.
It depends on the interactions for sure.
Whereas KF is about like the amount, like the chemical potential. So the amount of lithium I put in my box. Is that true?
That's true, except, it also depends on the mass of the lithium atoms, right? KF. So KF is determined by the number of atoms and their mass, right?
Sure, yeah,
Yeah,
but like
so-
if I just throw more lithium into my
You can
box, then
change KF.
Q naught is not going to change what KF will. Is that?
That's a great question. That's a great question. Yeah. So that's exactly this. Yeah. This ratio is really a dynamical property, and I don't know. Yeah. So that's some energetic question, right? So indeed, when you put more things in the box, they interact more, right? Because they have to be closer together, and indeed, you could get a different answer for the last spacing.
Oh, okay, so Q naught also could change.
I don't know.
The interaction.
It could be. It could be.
So can I have a scenario where like I have a square lattice, but then I throw more stuff in my box and that's not a square lattice?
I think that can be.
Okay.
Yeah, certainly. Yeah. Yeah, I think it can be. Or even the spacing of the lattice can change. Yeah. So I'm gonna step away from these difficult energetic questions. There are people who've thought hard about these kind of questions, and I guess using techniques that I'm not equipped to use. The thing I want to think about now is the critical theory, right? The field theory at the transition, okay? Which is much more of a high energy question, right? Much more of a field theory question. Okay, so everything else I'm going to say is about the critical point. Okay, so the first attempt is to do some kind of self-consistent RPA approximation. And so the idea is we want to understand the Green's function, or the inverse Green's function for the fermions, and the inverse Green's function for the bosons, and they're coupled to each other. And I'm going to parameterize that by, the free propagator, right? So if you set sigma and pi to 0, you get the free things. I guess if you set sigma to 0 and pi to epsilon squared, you get the free thing. And let's just think about how do they affect each other, right? So the self energy of the fermion, the leading contribution comes from this diagram, and which involves the product of the boson and fermion propagators, and the vacuum polarization, the self energy for the boson comes from this. It involves the two fermion propagators, and this set of equations is beautifully solved by the following simple power laws. So this was observed long ago by other people, or something related statements, that the self energy is independent of the momentum and goes like omega square root of omega. And the self energy of the boson is also independent of the momentum. And this is just the Landau damping. And indeed, so this self-consistent thing is resumming a subset of all the Feynman diagrams, which you could justify by some large N version of the theory. And one version that I know works is if you pretend that the boson is a matrix, and the fermions are incomponent vectors. Then this is the set of diagrams that survive. So if you believe this, we would conclude, one interesting thing we would conclude is that the specific heat at this critical point would be even bigger than that of a Fermi liquid. It goes, instead of going like T, it would go like square root of T. A very dramatic signature. But there's a problem with this conclusion, which is that if I use the scaling behavior that comes out of the solution, so actually it's very nice. It has z equals 2. Yeah, that's why the specific heat goes like it has dynamical exponent 2. And if I use that scaling behavior to ask, well, suppose I perturb this by some rho to the 4th interaction, that rho to the 4th interaction turns out to be relevant. It's a relevant perturbation of the fixed point described by this self-consistent solution. And I personally don't know a way of controlling what happens as a result of adding that rho to the 4th.
But at least at the level of 1 over n correction. Yes, it's true that large n corrections to this self-consistent one loop are small. But are they logarithmic? It's analogy portion of the same problem with hotspot and antiferromagnetic fluctuations. 1 over n corrections to self-consistent theory contains logarithms.
I don't know the answer to that, but this, even if the coefficient of this thing is suppressed by n, it goes somewhere, right? Even if the perturbation is small, it runs somewhere else, right? Some far away, which I don't know where.
There's not much, you're saying.
This is power law relevant. Yes. Yeah, so I don't know how to control this. And so this, this may have some, something to say about the physics, but we decided to start over. Okay, and the way we start over is the following. So I'd like you to think about this problem in the following way. So pretend that you're Wilson and Fisher in 1974, was it? Yeah. So you want to understand the Ising model in 2+1 dimensions, 3 dimensions total, and it's related. It's related to phi-4 theory. If you think, start at the Gaussian fixed point, and ask, I know there should be a phi to the 4th term by which I'm perturbing it, and if I just do naive scaling analysis, I see that the phi to the 4th term is a relevant perturbation, right? It goes somewhere. If I add it, it goes somewhere far away, and so the clever idea they had was, well, let's vary the number of dimensions. Right? Let's containable in the number of dimensions, and they observed that if instead the number of dimensions were four, then the phi to the 4th term is marginal. It's slightly below 4. It's slightly irrelevant, and so they can control the effects of this relevant operator by expanding around d equals 4 minus x. And then we find a Wilson fixed point, and it works very well, maybe better than it should, as we've been discussing yesterday. So we'd like to do something analogous to that. Okay, let's try to recapitulate their success. We'll see if we can. And let's change the number of dimensions. Well, actually, that doesn't do anything, because the modes that we're talking about, they only propagate in the directions transverse to the Fermi surface and the Bose surface. In fact, in this analysis, I didn't have to pick the number of spatial dimensions. It doesn't matter. There is something else we can do, though, which is we can vary the codimension. So this is something that other people have tried in related contexts. And so the thing I'm going to do is vary the codimension. So I'm going to add some fictitious dimensions, some fictitious spatial dimensions, which are transverse to both the Bose surface and the Fermi surface. So basically, what you could think about it, if I add one extra dimension. So if I'm really interested in a theory of 2 space dimensions, but I add another dimension, and what I've been calling the Fermi surface is actually a ring. Right? It's a ring in 3 dimensions. Right? There's 2 ways I can go to go away from the Fermi surface, and similarly for the Bose surface. I will call that codimension 2. And so more generally, I'm going to let the codimension be a continuous parameter C. So the picture of both the Fermi surface and the Bose surface is something like this. There's a vector perpendicular to the critical surface, which has C components. And the scale transformation. So let's think about the analog of the Gaussian theory in 4 dimensions in the Wilson-Fisher problem is again will be a Gaussian theory, and the scale invariance of that Gaussian theory acts in this way. So only the component of the momentum transverse to the Fermi surface and to the Bose surface scales. So that's how it's possible to have scale invariance despite the fact that there's a scale kf and a scale q naught. And so the action we're going to think about is a kinetic term for the fermion, kinetic term for the boson, the Yukawa coupling, the quartic term, which the whole reason we're doing this is because the quartic term was relevant. So we want the quartic term to be, we want to find C such that the quartic term is marginal. That's the analog of the upper critical dimension, the upper critical codimension. And then of course there's the term R that we're varying through the transition. Please.
What happened to rotational invariance in this study?
Indeed, there's still exact rotational invariance in the real direction.
In the real direction, not in the full theory.
Well, I guess it's also rotation invariant in the perpendicular space.
Fix out the.
I do.
You do, and then you're breaking it by that choice.
I'm breaking. So I'm not breaking the symmetry that I care about, right? The thing symmetry
You care about physical symmetry, but
so I'm adding extra dimensions,
which are being treated so differently, which therefore there's not rotational symmetry in the full system.
Yes, that's right. I'm not making the symmetry bigger.
Integration transforms to form surface move the dimension.
Yes.
I mean, it's consistent. I'm just making sure I understand what's going on. Yeah.
So in this expansion, usually there's a symmetry that is like more crucially broken, which is charge conservation. Usually they're the side dagger terms that appear when you vary the codimension of the Fermi surface.
Mayo, there are no such terms. No.
Okay.
No. Yeah.
Sort of related question.
Yeah.
Why is there an advantage to this expansion over the one that you and David Ross engineered, many years ago?
So you're asking about, good. So indeed, so we tried in the RPA varying the powers in the dispersion and to make the thing marginal. And maybe there's a way to get it to work. I don't know.
Probably need more than one upset.
I think so. I didn't see how to control it. Yeah. Okay, good. Okay. So let's analyze the scaling of the interactions under the scale transformation that I just defined. And so the analysis of the boson self-interaction is very similar to Polchinski and Shankar's analysis of the four Fermi interaction in the Fermi liquid. And the key thing is, and as in that case, there's a distinction between interactions where the kinematics are generic, where I just pick four random vectors and ask how do those modes scale. And the key point is that if you write the whole thing in the momentum space, the question is about the scaling of the delta function, right? So there's some delta function that imposes momentum conservation. And if the delta function is constraining scaling variables, then the thing is more relevant than if it's not. And so for generic kinematics, the delta function spends its life constraining non-scaling variables, and the dimension is 2 minus c. Whereas for forward scattering, which by Bose symmetry is the same as VCS, because rho is a real variable, it's more relevant and its dimension is 3 minus c. Okay, so remember that 3 minus c. And let's think about the Yokawa term. A similar thing happens for generic kinematics. It has this dimension, but if we ask about the scattering, which keeps all the modes on the Fermi surface, its dimension is instead 3 minus c over 2. And so as you can see from this formula, if we set c equal to 3, both the Yokawa interaction and the rho to the fourth interaction are marginal. So that's the upper critical codimension. There's one slightly funny thing, one slightly unsavory point about this, which is the kinematics of this cubic interaction, of the Yokawa interaction, are a little funny. We can't exactly set the points to all be exactly on the Fermi surface. Something funny also happens in even in the Fermi liquid case, but instead the thing we do is constrain the angle of the scattering between the fermions to be equal to this theta naught, this parameter that we introduced. And the constraint, it's actually not a delta function, it's the square root of a delta function. What I mean by a square root of a delta function is divide up the Fermi surface into points of separation d theta, and square root of delta function just means Kronecker delta over square root of the distance. Okay, and so the marginal interaction I'm going to introduce, we'll have some matrix here. Yeah, we'll see that in order to introduce this, extend the codimension of the Fermi surface, we need to introduce some spinor indices. And so this matrix is a matrix in those spinor indices. And for some choice of this matrix, there's a symmetry under which a rho is odd. And moreover, the Yokawa coupling is invariant. And so if this is a symmetry, it forbids the terms that are odd in rho, and particularly the cubic term, and it forbids varying the Fermi level away from the nodal surface. So I'm going to assume that. That's how I'm going to ignore the cubic term. We can talk more about where that might come from physically. Okay, so I guess I have 5 minutes left. Is that right? Okay. Roughly speaking, I mean, because we nice to have time for some questions. Then definitely, yeah.
I mean, plus or minus, but yeah, I mean.
Okay. So
Many slides do you have? Say that.
I think I prefer not to answer that question.
Okay. In that case, then be careful and say 5 minutes.
So yeah, Tarun and I have been working on this project for a long time, unfortunately, and there have been I don't know, maybe at least 4 or 5 times when we were about to give up on the project. And one time was the following. So we wrote some naive kinetic term for this nodal fermion, and we did the whole RG calculation, right? We found this upper critical dimension that I just described. We did the whole calculation. We found the fixed point we found the beta functions for Yokawa coupling, the beta function for the rho to the fourth term, And, they had beautiful fixed points, like one might hope for in one's wildest dreams. But then we noticed that in the renormalization group, we also renormalized the velocities. So basically the coefficient of the dispersion transverse to the Fermi surface compared to the one in the plane. And there's a velocity for the boson and a velocity for the fermion. And the beta functions for these velocities depend only on the ratios of the velocities. So they impose two equations on one variable, the ratio of the velocities. And we found that they didn't have a solution. And so we spent, I don't know, we spent a week or so, feeling sorry for ourselves. And, because who cares about the velocity, right? It's just some dumb number. Well, okay, you care about it, right? Yeah, no, of course, yeah, right. The fact that there's no fixed point means that, yeah, there's no fixed point. The velocity runs off to infinity, everything becomes singular. And then we realized that the kinetic term we were using for the nodal fermions was not local. It's not something that you could, its Fourier transform is not a local action for the nodal fermion. And so we thought, well, okay, let's do it right. It'll change the answer. Let's see what happens. And so we learned more than I ever thought I would know about the theory of nodal lines, meaning a Hamiltonian, a lattice Hamiltonian whose low energy dispersion has this ring of zeros. And so this I got from literature on there's a big literature on nodal lines, but there's actually a very nice way to understand it. Essentially, it looks like the Dirac Hamiltonian, except that with the tricky part that, and so when KF is kind of like the mass in the Dirac Hamiltonian, with the tricky part that the gamma matrices don't all anti-commute. Some of them commute with each other. And that's why you get this nodal surface. And okay, I'm gonna have to say this very briefly, but we figured out how to project onto just so this has 4 bands, but we figured out a way to project onto just the bands that have the nodal line. And we found the propagator for just those bands. And we found an action whose propagator that was, which is this thing where these gamma matrices with the theta are slightly funny things. They're just a collection of finite dimensional matrices that depend on the direction of the Fermi surface, and they satisfy this, what I think is kind of a nice generalization of the Dirac algebra. So rather than commuting to delta function, they commute to a projector, the projector onto these 2 bands. Okay, and so the crucial thing we need for doing our loop calculation is these, the analog of trace identities involving these new gamma matrices, which okay, we figured them out. Okay, so now in the last 1 minute, I can quickly tell you the structure of the RG calculation. So the boson self-energy, you can see this is the bare kinetic term. You can see that the relative coefficients of these 2 terms gets renormalized. That's why this velocity runs. Similarly, for the fermion self-energy, the relative coefficient of these 2 terms gets renormalized. The fermion velocity runs. The vertex correction is exactly 0 at 1 loop. It's because of the following geometry problem. If I pick these 3 momenta to all lie on the critical surfaces, so that specifies 3 vectors with certain lengths, is it possible to choose a vector k1 that's also on the Fermi surface and conserve momentum in the loop? And the answer is no. This is to be contrasted with what happens in the calculation for a commensurate spin density wave, where twice Q0 is equivalent to 0. And so there is a vertex correction in that case. I suspect that there is a vertex correction at higher loops, but we didn't calculate it yet. Okay, the calculation of the running of R is very simple. The calculation of the running of the 4 fermion interaction, of the 4 boson interaction, it's not so bad. The analog of light by light scattering only contributes when the bosons are at certain angles relative to each other. That's a little bit interesting. And so here are the beta functions for the velocities. And now we find 2 equations for one unknown, which are the same equation. So I don't really know why this happened, but yeah, I feel like, we were rewarded for our good behavior of using a local action. Okay, so this fails if we use a non-local action, and the beta function for the 4 boson interaction has a controlled fixed point, and the beta function, the beta functional for the 4 fermion coupling satisfies this equation, which indeed also has a fixed point. It's a pretty interesting fixed point because the interaction depends on the angle between the bosons, and it's big at these values where the light by light contribution appears. Okay, so we can calculate critical exponents. They depend on this dimensionless ratio. It's pretty weird. They depend on this Q naught over KF. So I got to stop. Let me just make a few comments. This is a very gapless theory. One sense in which it's very gapless is, in addition to the log violation of the area law of the entanglement entropy from the Fermi surface, at the critical point, the Bose surface also contributes a similar log variation. There is a theorem due to these folks that says that any compressible state with the Fermi surface has to have a symmetry bigger than any finite dimensional Lie group. The thing that usually happens is that points on the Fermi surface decouple from each other, and the particle number at each point is independently conserved. This is called LU1 symmetry. And so we can ask whether this critical point has such an LU1 symmetry, and I think that it cannot. So their name for a system that has this LU1 symmetry is an ersatz Fermi liquid. And I think our system is a non-ersatz, non-Fermi liquid. Yeah, so I don't know the resolution of this. Okay, maybe I won't say anything about this. In the higher dimensional analog of our calculation, we didn't do. The RG I described was only in the case of 2 spatial dimensions. In higher dimensions, it's even more interesting and is waiting to be done. I'm not sure if I'm going to ask my students to do it, to think about it. I don't know. And then finally, okay, in the last -3 minutes, a very natural question is, where might we see signatures of this transition? And maybe the best candidate is the following. So, people have been, there's a lot of excitement in the condensed matter literature about twisted, about Moiré systems, where the interesting thing about it is that, well, okay, actually, I don't need the Moiré. Sorry. Let me think of, so yeah, there's these experiments on multi-layer graphene where actually the Moiré potential, where the electrons are is very far from where the Moiré potential is big. And they see a phase diagram where there's a Fermi liquid phase, and with actually it's a single component Fermi liquid, and nearby something that my colleague Daniel Parker assures me is a Wigner crystal, and who knows, maybe this is a continuous transition. Yeah, the idea being that the underlying lattice spacing is much smaller than the lattice spacing of the Wigner crystal, so maybe we can ignore the fact that it breaks rotation invariance. Okay, let me stop there. Thank you for listening.
I'm gonna use the position, we have to run a couple of minutes. Mine is very quick. It seems like to do the analog of the epsilon expansion here that you introduced, you have to extrapolate pretty far, right?
That's right. Yeah.
By
rather
3
than
instead
setting
of by
C-
1.
Yeah.
Is that potentially
No,
alarming?
two instead of 2. Instead of setting, epsilon equal to 1, we set epsilon equal to 2. Yeah, we want the potential should be 1.
Okay.
Yeah.
Right. Thank you. Sorry.
Yeah.
So
Indeed,
is
two
that,
is very
so here you have this nice picture, but like to apply it,
Yes.
so you
Yes.
might one worry that this just evaporates along the way?
Yeah.
Oh, sorry,
Yeah.
that's the slide.
Yeah. So indeed, if another possibility is that the conclusions from the small epsilon expansion just don't apply when C equals 2, and the other possibility is that we just don't control the running of the row of the fourth term. Yeah. And if the row of the fourth term becomes big, the thing that happens probably is that the critical point is surrounded by some ordered phase, some pneumatic phase, something like that.
And what is the self-energy at the end of the day at this point?
Well, okay, there's logs, right? We computed this exponent, and what can I say about it? Well, let me just say it's not
omega, which goes with omega. We started with omega 1/2.
No. Well, here, I mean, we're starting at C equals 3 with omega to the 1.
Well,
Right.
but then we have correction.
That's right. So this is the first correction to that. Yeah.
Sorry?
Yeah. The thing we computed here is the first correction to the.
So it's omega to the power 1 minus something of order of magnitude.
Yes, that's correct. Whether it has anything to do with omega equals 1/2 when we get to C equals 2, I don't know. C equals 1, I don't know. Yeah. Right.
I have many questions, so maybe I'll reduce to the clarification question. So what ultimately happens to the running of the velocities?
There's a fixed point. Yeah, yeah.
So they, but do they run small, do they run big? Is it just the ratio that runs?
Only the ratio runs and it's set to it's determined by this angle theta naught. Yeah, it's very nice.
And, did you ever look at transport?
We have not yet looked at transport. Yeah,
If it
Bell,
says 5-4 is running to a finite value, maybe there's some interesting universal resistivity or something.
maybe. Yeah, we've been very concerned with, trying to convince ourselves that the fixed point exists there.
That's the importance of it.
Yeah. Yeah, Dominic else has been trying to convince us to compute the shear viscosity.
He's doing, that sounds like fun. There are maybe easier things to compute.
Maybe, yeah.
I guess kind of related to what Alexi was asking, so if you can't really consistently extrapolate to codimension 1, are there physical systems or interesting systems with codimension 3?
Great.
I guess they would have to break rotational invariance like he was asking earlier, but.
Well, right, so indeed, like I said, there's a big literature on nodal lines, right? Systems with fermions where there's gapless modes on some line or some higher codimension locus in momentum space. And we can ask about phase transitions out of such things. And I think that, the technology we developed to find the propagator for the nodal fermion, I think should be very useful for such questions. Yeah, indeed. Yeah.
Maybe in that vein, another clarification question. So you talked about this and, in the context of like a sort of crystallization transition.
Right.
Is that important or is it just that I have to have some scenario which gives me this critical
Right. The important thing is that there's some bosonic mode that wants to condense at finite momentum, and it hasn't picked the direction. So the fact that it was just the density, I think, is not crucial. So indeed, so you'll notice that I imposed this Z2 symmetry, which is maybe not so natural a symmetry to impose on the density, since you could just add some more particles and then the zero of the density changes. So actually, I think maybe the best candidate that we've thought of for a system with the same physics that realizes that symmetry is if you have a bilayer system where the mode rho that I'm talking about is the relative density of the two layers, and there's a symmetry between the two layers. So then obviously the relative density is odd and they're interchanging. And yeah, so this kind of situation where you condense some excitons at some non-zero momentum, I think is
finite element compensation of
yeah.
But extending the same question. If it would be spin mode instead of chat mode,
Good.
story mode is the same.
I think so. Yeah. We got a little confused about the Z2 symmetry in that case, but I think so. I think spin also. Yeah, but it's very important that we're in the continuum. Yeah, that we can ignore any underlying lags that would break the rotation symmetry.
Okay, any further questions? If not,
Thank you.
let's thank John again.
Then I'll be back.
Okay, yeah.
Oh, right.
So let's set another round.
Sure. Finally, doing.
Yeah.
I will get to the home.
Okay, thank you.